Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This time we will be going over Mammon Machine, which is the tool that I built for making Super Nintendo demos. Particularly, this tool covered the demos we made as the group Elix, that's Citrix and I, and also Alien did a lot of graphics for the second one we did, so those demos are new, and Smash It. The Mammon Machine kind of covers a lot of the tech that went into both of them, but really the tech that kind of went into the first one is really just an earlier version of the tech that went into the second one. And the fact that I ended up doing video compression with it is kind of has a lot to do with how it works. So what I wanted to do this week is kind of give an overview of that tool, but I realized that because I don't have like a lot of test projects or anything with it, I only really have the demos that we made with different versions of it. It makes the most sense to actually just go over, like do a breakdown of one of the demos and then show how that technology is actually used in that context. So I figured we'd do that. And particularly, I could go over one of two demos. I could either go with new or I could go over Smash It. And Smash It is a better one to show off the tech and kind of the goals of what that tech like is meant to accomplish. And so we're going to go over that today as well. And then next week, I want to go over how a lot of this same tech was utilized to do video compression in the demo new. So that's basically what I think we'll do today. Now, as usual, I didn't really prepare for this, so it's going to be a lot of just kind of jumping around with things, but looking at some cool stuff, and I think this will be pretty fun. So hey guys in the chat, by the way, Trilater, Soda Design, Lord Jonel, John Hunter Nye, Daniel Collin, how's it going, guys? So on the screen over here, I have basically the demo Smash It running in basically a preview mode, which is what I use to actually sync the demo. So basically the setup I have, just to kind of show you what I'm working with here, let me kind of arrange the windows in a way that makes sense. With limited screen space, it's a bit tough to show a lot of this, but we're just going to have to deal with that. So, excuse me. So what this window up here is, it's basically a two-part preview window. So on the left, you see what the demo is going to look like. And on the right, you actually see a visualization of here is video memory. And then there's a small bar over here, which is the palette memory in the Super Nintendo. So for example, I can move around here. So this is Ableton Live, by the way. And as I move around in time, it'll actually move around in time in the demo. And generally that works pretty well, although there's some sync issues because we actually sync the two things with MIDI. How's it going, Vince? But basically, the idea is that I would write the code in something .NET-ish, particularly F#, and then be able to sync it and stuff like this. Because, for example, we want to do like, actually, hold on, I don't know how loud my system audio is. This might be a bit loud, but nothing else that's loud, probably coming through the mic. But the idea is that I would be able to sort of write the effects in something like F#, and then come into Live here and actually sync them. Generally, that works pretty well. But yeah, we'll kind of talk about how that works and some of the different effects in this demo. Before that, though, I figured we should watch the demo. So let me go ahead and pull that up. Pull it up in a little emulator. Whoops, that's the wrong tab. Studio C, how's it going? So again, the demo that we're going to watch here was released in 2014. It's called Smash It, and it won the old school competition at Tursock that year. Made by, I did all the code, Citrix did all the music, and Alien did most of the graphics. So I'll watch that in a sec. Oh, hold up 1 second. John Hunter, can you compile F# to SNES? Nope. Something a little more weird than that. Hold up. That should work. Yeah, so that's Smash It. Pretty cool little demo. Couple questions. Studio C, is there any special reason behind choosing a functional language? I was learning functional programming around the time I was designing this and came up with a really cool way to utilize that approach. When we get into some of the details of how this works, I think you'll see that it makes sense. So you see, I see some bragging like in the old times. Oh, yes. There were a couple other groups around the same time that were talking about doing SNES demos, and they still haven't. So I'm happy about that bragging. Daniel calling awesome music. I agree. John Hunter, is that mode 7? A couple of the effects in here are mode 7. I guess you're talking about the rotating thing, and the short answer is yes, but the longer answer is not all of it. Vince didn't know you were doing some SNES music. That's awesome. Yeah, I got to get back into Super Nintendo stuff eventually, but it's a bit backed up behind other projects. Yeah. So basically, a little bit of chronology here. Typically, when you make these kind of demos, the way you do the different effects is you basically write them as if they're like their own program. You kind of write each one individually, as if each one has like full control of the CPU and everything. This is kind of coming from an approach that you would have from like the 8-bit systems in particular, where you just kind of write each thing as its own sort of separate program, and then each one would just kind of run for a while and do its thing, and after a certain number of frames, it'll load the next one for a couple frames, and then it will jump into the next effect, all while like playing the music and stuff in the background. And as I was doing that in late 2013 or so, I made a few different effects I played with. For example, I did this Manger sponge zoomer that it was kind of cool because I could get it to like it was a roto zoomer just using mode 7. And I did all the math so that it would like match up, so it would rotate and zoom to a certain degree, and then it would be self-similar again, so then it would like repeat the zooming. So it looked kind of cool when it would actually go through everything. And I tried a couple other things, but overall, I just really didn't enjoy working that way. And in particular, I was like in my demos, a lot of the things that I spend a lot of time on are like sync and like screen flashes and stuff. And I really didn't want to sit there and like do cycle counts by hand to do that kind of stuff. So I started thinking about, okay, when I do high-end demos, I use something like Rocket, which would allow me to change values over time. But how can I make that workflow good with Super Nintendo? And I thought sort of the ultimate tool that I could have would be one where, okay, I'd have some CPU-based effects, but really all the CPU-based effects are doing is sort of shuffling around data that it will eventually upload into a certain area of like VRAM. And it would do that like every frame, but that's like what the effects do mainly. But at the same time, there's all those other concerns like, okay, yeah, we also need to change some register values or maybe some palette memory values over time in order to sync stuff. Between effects, we need to load the next effect. So like, it would be great if I could, for the CPU effects, just focus on like what like the code the effect would actually do, and then come up with some kind of system that would guarantee that the stuff that this effect expected to be in VRAM, like the graphics data in particular. For example, like a plasma effect might have the graphics data all pre-calculated and in video memory, but then it would display different tiles at every part of the screen, and it would figure out which of those tiles to use on the CPU every frame. So the idea in that case would be I would have some system that would automatically make sure that that particular tile data was already in memory, and then I would just change the map and upload that every frame. And when thinking about that, so I kind of had this idea of this half tracker thing, half emulation based thing, because there was also for debugging in the Super Nintendo, the hardware is very configurable. So like you can put graphics memory basically anywhere in the hardware with some limit, or anywhere in the video memory with some limitations. And there's so many different palettes you can use and so many different things. It's just a lot of kind of registers and bits to wrangle. And so I thought that it would also be nice if this particular kind of tool had like a video memory viewer. So when I was thinking about all this, I basically came up with a way to, like, if the interface was every frame, I would call some function. And then when that returned, I would go and just do whatever my effect needed to do. And that function, again, would talk to whatever my sync system was and guarantee that whatever I expected to be in video memory was in video memory, and would allow me to control when things were loaded, how long they might be loaded. Eventually, that would be cool to make that automatic, but I kind of figured that would be pretty difficult, so I'd rather just have some fine-grained control over that. And what I came up with was a system where the way this would work is you could basically have, like, because the demo would always run the same frame rate, it would basically always run the same number of frames. And when you think about that, you realize that you actually have per frame, like in that case, you have, because I'm talking about demos where you'd actually sync to music, so this would actually be the case. It wouldn't just be like, oh, it'd play this song and this music for a while, and when you hit space, it would go to the next one or whatever, or press A, I guess, in this case. And so the demo would always run the same amount of frames. And so I could basically, if I had a system that would allow me to work with this stuff, then I could basically schedule everything. And so what I came up with is a basic system that would allow me to, it basically would be bytecode based. So whenever I call into the function, there would be this pointer, and this pointer would be in some data stream, and it would look at that and say, like, interpret this data as instructions. So for example, there would be a update this register with this value instruction, or there would be an end frame instruction. So I would do that every frame, and then before, like when the demo is being built, then I would just sequence all these. So you basically have this kind of like animation and scheduling data to just move all the bits around. And then after you deal with that every frame, and of course most frames would just be like, okay, end of frame, and that's all it would be. And then your effect would actually just focus on the data that it would need to change on the CPU. Now the funny thing is that this actually ends up being so general purpose that I have yet to do any CPU-based effects. Because I've been mostly focusing on sort of making this tech, and then by the time the demo comes along, it's like in 3 weeks, and then I don't really have enough time to do any of the other stuff, so I just end up trying to find creative ways to use this. And that ends up being really fun, right? And so as a consequence of that, a lot of the data preparation that I've done here means that, okay, I do the effects in F#, and then everything gets kind of compiled into these little bytecode that the demo will load and run every frame. So that's kind of a high-level overview of what we're looking at, and then we're going to look at some details about how that works. But I'm seeing a lot of stuff in chat, and I'm not responding to that, so sorry about that. John Hunter 9, I'm trying SNES music, but I can't get the samples in tune. Interesting. I have no idea what the problem might be. I do know like sample or like the loop points have to be aligned to certain sample boundaries. So it's possible that, yeah, it really depends on your sample for what that means. But usually you have to like adjust anyway. A few semitones, if not more. Bin94, most of the stuff I do is in a ROM hacking tool for Earthbound. It's essentially a fully functional tracker. Oh, that's pretty cool. Do you know how to program the cutscenes? I heard that's a mess with Earthbound. The hacking tools are easier to use now. Everything gets direct and ROM. That stuff's really cool. I'm guessing that I'm not that familiar with how a lot of those like cutscene systems work on a lot of those older games, but I'm guessing they're actually very similar to the tech that I built here in terms of like there is some kind of scripting language, which ends up being some kind of bytecode that's interpreted. Because it's a pretty natural approach to that kind of problem. And it basically means you can do whatever you want to actually generate that bytecode. And I just happen to use this F# thing that I can show you, but it's yeah, pretty strange. So what I have here in the stuff when I went over the tracker, I went over this thing called ASDK, which is basically my assembler and everything. And that's its own thing. So there's basically an assembler here. Then there's Mammon Machine itself, and Mammon Machine is just sort of a general name. By the way, Mammon Machine comes from Chrono Trigger, which if you haven't played it, it's the best game ever, and very appropriate for some kind of tool that helps me make SNES demos. But it's basically a collection of a bunch of libraries, and they're all meant to be sort of consumed from F#. So for example, one of the libraries I have here is graphics, and that has things for like color. Let me zoom in a bit here. Has types for dealing with color, applying a unary operation to a color, clamp color, multiply color, add div subcolors from RGB 255, brightness, all kinds of stuff. So this is all just about working with colors because we're going to be doing a lot of stuff with, in the demos, we're going to be doing a lot of things like loading an image and maybe adjusting its color or like doing screen flashes. So we want to be able to work with colors. We have a frame buffer, which actually is not used directly by this thing. I can get to where that's used later. A couple other things that I'll skip, like a median cut filter, which can do like dithering. We have one that just deals with tile encodings. So if you give it a frame buffer, so the idea is that we would load like a bitmap and we get a frame buffer back. And then we would have this system here, this tile encoding thing, encode, I guess, a tile. So we have an X offset and a Y offset and a palette, and then a frame buffer, and also the number of bit planes that we're going to be using, and it'll actually encode the tile. By the way, if I forget how some of this stuff worked, which will probably happen, it's because I haven't opened this project in like 3 years. But it still should be pretty cool. Bin94, yeah, stuff like move by X tiles or move to map coordinates. Yeah, I think you'll like the little bytecode that I have here. There's a SNES bitmap here, which yeah, just has some information about this, like width and height. It has its own whatever its palette would be. It's tile data and it's map data. You can get from a frame buffer, you can get a SNES bitmap. It might fail. You can also go the other way, SNES bitmap to frame buffer. A couple of these other things, I can get them from streams. That's how we load them from files. All this stuff is in the context of like, if I were to just write an F# program that could like load images and save images, you know what I mean? Like just do image conversions. This would be a really useful tool. We also have a mode 7 bitmap because that's a slightly different encoding. So there's some things there. And there's a mode 7 matrix, which we actually use to do the scaling and rotation. So to design, why not use the SNES tracker to sync the effects? Because then I would have to rewrite like a lot of the glue code. So it would be better to just use an existing tracker for that purpose, or something like Ableton Live, which I end up using through MIDI, which I didn't actually work that well, but yeah. Anyway, Mammon Machine Graphics is just a collection of a bunch of stuff for working with graphics. We also have, and MISC probably isn't very interesting. we have Mammon machine emulation, and this is where stuff gets kind of interesting. So basically, we have an emulator. Now, an emulator in this case is not an actual Super Nintendo emulator. It's really just an emulation of the video hardware. So with the system that I described earlier, you'd want to be able to basically describe the state of the video hardware at a given point in time, and then have some kind of system be able to generate the bytecode that would get you there. Does that make sense? How that would be convenient? So that's kind of the headspace you want to be in here. So what this emulator actually does is it takes a description of that state, which would be here, and that just contains like a bunch of register values for what the hardware would look like, and it'll just produce an image, is sort of the idea, right? So, for example, this state would look like this, and there's a bunch of to-dos here. Ignore those. But the idea is we have different data types for screen mode, BGMap size, BGMap location, all these different values. And I model these values specifically instead of just with numbers in order to just make sure that we're always bounded for what these are. Because typically you want to pick specific values anyway, and the fact that you just get a list of valid values is really helpful here. And also that it maps to what it'll actually be like in VRAM. When you see how this is used, you'll see that this will actually make a lot of sense. Bunch of other data types for modeling different pieces of the hardware. The entire state of, for example, a sprite, or like an entry in the object attribute memory, the object memory, I guess you could just say. Different HDMA targets. And this isn't entirely exhaustive. There's a bunch of stuff I don't handle right now. Like there's a couple video modes that actually they use the map data to like shift tiles. A couple things like that I just have not done yet. And there's some blendings. Maybe I cover the blending stuff. There's some features that I haven't. Oh no, it was when you have BG maps of more dimensions than just the regular size. I also haven't handled stuff like that. But basically we cover a lot of stuff. So we finally get to the actual type itself, which is the SNES state, which is actually, again, a SNES hardware state. But we have like a Boolean for whether the screen's enabled. We have a screen fade value. We have a screen mode. And then we have all these different attributes for BG1, BG2, 3, and 4. There's the mode 7 matrix and the mode 7 center position. We have sprite sizes, the base of the sprite memory. Sprites on the main screen enabled or sprites on the subscreen enabled, because there's some blending stuff. So it's just this really exhaustive data structure that would give you that. We also have some conversion functions to help here. Get actual values for what the register values would be for different things. And yeah. We also have like a default sprite state and a default state, and this will contain sort of default values for all this stuff. So that's basically what this state is. And the emulation stuff in here really is just a function from that state to an image. So in addition to that, there's a bunch of tests here, which just test different pieces. And so what I did is, like during that summer, as I was building all this, I would always just come up with a new state that I wanted to include in that data structure. And I would do some tests against the hardware and in the emulator. And I would just set some registers to some certain values. And I would test on the hardware and again, an emulator. And then if it worked, then that would be great. But the idea here is that this test emulator thing would basically so we give it a SNES state. In particular, this is the default state. With, which is a syntax in F#. So you basically make a copy of this data structure, but then you set all these values to be different ones. So this is a very convenient way to actually just create these states. Just a nice way to write it. So basically say it's the default state with the screen enabled, and the screen fade is this screen mode, this VRAM, and this palette, if that makes sense. And then what it's going to do is it's going to look on disk for basically the name of this test. There's a folder with a bunch of PNGs in it. In fact, I can bring that up. And it's basically going to take the state that I made and compare it to a PNG file on the disk. If they match, that means our emulator is still working for that case. If it doesn't match, then if it doesn't match, there's a couple things that happen. First of all, it doesn't find a PNG file that matches that test, which is often the case when you add new tests. And in that case, it'll show you it and then ask you if it's correct and basically tell you or ask you if you want to create a new one or not. or like if you want to save the current output to that file. That's what I mean by that. And then the other case is that the images don't match. And then it basically shows you both and says, okay, is this one correct now and you were wrong previously? Or is this just wrong or whatever? So that's basically the idea there. 1 second, let me pull up what these look like. Because I did a lot of tests for this stuff. But it's kind of cool. Michael C. Anarchy, how's it going? Well, I guess not too well for Michael C. Yeah, I think it's in refs. Maybe I can't actually, because it looks like these are just binary files. I thought they would be PNGs or something. Yeah, so I guess I can't pull that up. Sorry about that. I'm pretty sure I'm able to run the test, though. If I just run one of these. And maybe I can delete one of the refs. Oops. Oh, yeah. Did I do... What is going on here? Unable to start debugging. That's new. Well, not terribly important. Mid-94, and this outputs code a SNES can run. So I'll get to that. So what I've covered here just has, like, we have from F#, we have a way to describe a SNES state. And we have something that'll actually give us a visualization of that SNES state. So when I run this, for example, this will hook up to the sync tracker, and using some inputs will generate some SNES states, and we can see the SNES state here. There's actually... didn't look like it loaded stuff. There we go. So these are both three visualizations of different piece of that same state, right? So there's this is the output of that emulator thing that I mentioned, and then this is just a visualization of the video memory, and then this is the color memory. Right? Now, once we have a way to generate those states and visualize those states, then what we want to do is we want to be able to basically generate a bunch of those states for every frame that the demo is going to run. And then what we can do is we can have a pass that goes over all those generated states, right? And this pass would take, okay, we have a known starting state, which represents the state of the hardware at startup. And then for all the frames in the demo, we're going to generate a little piece of bytecode that represents all the changes that would have to be made to take the SNES from the state that it's currently at into the state that is described by that data structure. Does that make sense? So the reason we do this again is if we wanted to like be able to sync everything in the demo, then we would have over time, we would have all these sync tracks. So for example, when I always have a hard time explaining this because I feel like there's a lot of context that you kind of have to have in your head to really get it. But what's cool about it is that if you understand kind of the motivation for it, you can see that it's really nice to have this. Especially in combination with CPU effects, but we actually haven't gotten that far yet because we haven't had to. But basically what I do is I have an F# program that, given an input time, can give me a Super Nintendo state, right? And then using tools like Ableton Live, I can just have it sitting there running in a loop. And so it's always generating a state and then displaying it in this window, right? So this is kind of the way I work in the demo. So I'll go and I'll change some F# code, which will change the function that this... that's used to generate this state. And then in Ableton Live, I can like move around in time. I can sit here and tweak values. So for example, here, if we go to, where is it? If we go to, so this is a different part selector, for example. There's a screen flash that's done here. If we go to the X vectors, which is this particular effect, we have a bunch of parameters for that. And there's a couple things, so like start Y and end Y. I can sit here and tweak this in live. You can see this is where that effect starts. And NY, we also have this distortion value, which distorts the top and the bottom. So I basically sit there and automate those things over time, just in something that I'm familiar with. And these are communicating, right? But again, the whole thing that's happening is that this is just running in this loop where it has a time value, and time, it comes from Ableton Live. And every time it's just generating one of those SNES state objects, right? And that's being output here. So we just need some F# code to generate state objects, and then we have a way to get like sync track values that is used to generate those state objects, right? So that's what I'm working with here. And in fact, when it's playing music, it's actually just playing music at Ableton Live. At the bottom here, I have just this music file here. When I'm done with that, what I want to do is I want to take all this and I want to basically sample that function for every frame that would run on the SNES, and then generate bytecode for all those, for every frame. So that's sort of the next thing that I want to show. Daniel Collin, but you also could have used Rocket for this as well, right? Yes. In fact, the new actually used Rocket, but that was a little bit different. This used Live because I thought that would be more comfortable, and for the most part it was, but it has a bunch of glitches. Like sometimes if I let this play between effects, the loading stuff doesn't always work, and you'll get like here, you get like half loaded stuff. I don't know if you'll be able to see it again. Here it is, like this line here. That shouldn't. Oh, there it worked. But yeah, so there's actually, and it has to do with the fact that I end up communicating with Live via MIDI, and it ends up sending MIDI events out of order sometimes. So there's like, I have this loaded amount thing for different tracks, which I'll get to, and sometimes those go out of order, which means the stuff isn't actually loaded all the way into video memory. So it actually kind of sucks. But we tried it. That was the idea. We had to try it for a demo before we knew that it would be that bad, and it was that bad. So I'll probably go back to using Rocket actually. But it really could be anything, because it's all just inputs to that function that's going to generate states. So then when we have that function, like, so basically working on the demo is working on that function that given time, it'll give you a SNES state. So we may want to change what images we use. We may want to change the value of the flash parameter over time, all that stuff. And so we work on those, then we get this program. Then what we do is we want to actually take that and then generate all of the opcodes that will actually run on the SNES at runtime. So this project, which is futuresjapan.content. Futures Japan is a music style I was into around that time. don't need to think any more than that. I have this content project that actually contains all of the functions that'll give you SNES states. So for example, the X vectors effect. That's probably not a very good one to look at right away because it has a lot of stuff. Where's one? Like the Elix logo is a nice one. So it actually, when you call this function, actually gives you a different function. But the idea here is that there's a function from the previous state and the state of all the sync tracks. And we get like the time, we get the flash value, we get some data amounts from different tracks, get these tile locations. And we just say, okay, we're going to make whatever the previous state was with all of these values here. Just set the ones you care about. And that's it. So that's what a simple one would look like. Then more of the complicated ones, of course, will do a little bit more data processing, typically on startup, but also sometimes it's dynamic. Just a lot more data preparations, which is why we have these libraries for working with this stuff in F#. But it's basically the same thing at the end, where given a base state, we're going to figure out the new state. In this case, we have a bunch of HDMA lanes that are working, all that kind of stuff. Drew 2, so when you start a new project in Ableton, all states for the entire timeline is the default state, and then you select the time in Ableton and you modify the default state, and your app is constantly saving that state out. Not quite. Not quite. Maybe I didn't understand you correctly, but I don't think so. So the idea is that I'm going to continue explaining it the way I understand it, and then we'll see if we can reach an understanding that way. instead of trying to bridge the gap, if that makes sense. So I typically work by running this project, and this just, if we look at the top level code, so it creates an MU window, it creates a sync object, and so this just syncs with something over MIDI, which happens to be Ableton Live, over this virtual MIDI port called SNES port. We have config, which we use Europe because it's going to be a PAL ROM. And then the demo is create demo from the config, which will basically give us the function that we need. So that's actually what this gives us. So now while the emulator window is open, we're just going to get a new state by calling the demo function on a sync state. So we grab the state from the MIDI sync stuff, give it to the demo, and it will give us a state. Pretty simple. And then we're going to tell the window to reflect that state, and then we just sleep for 5 milliseconds. So that's pretty straightforward here. You'll notice this is also the BPM. It's actually slightly off, not exactly 128, and that just has to do with the resolution of the timer. That in the tracker we said we wanted 128, but it ends up being closer to about this. I think I just got this from trial and error. But this is all that's actually happening when I'm sitting there working in the demo, right? So if I want to change the code for an effect, I go in this F# stuff and I go in some, change some value, and then I rebuild this. And then we'll get our emulator window open again. It takes a minute to start up because it's processing a lot of the data for different effects, and then now I can jump around in Ableton. So for when I actually have to change the code, I may do that. But then, for example, if I'm changing some of the sync stuff, so for example, the flash value here, I can just pull this up in Ableton. And that was kind of the idea, is that I'd be able to use this kind of tracker here. That seems wrong. But I probably just changed something I shouldn't have. Oh no, it wasn't loaded all the way. So I sit there and work with that. But then when we're ready to pack up the demo, we have a different thing here. Now this code may not be as straightforward as I remember. So give me a second. I think the anim test module actually has all this stuff. Vince94 makes me think of editing effects in the timeline with Premiere. So that's kind of the idea, is that for a lot of these parameters, I want to be able to edit them in a timeline like that without having to do like frame counting, because I don't want to do that. And then it would just work on the SNES. Like all that stuff would be taken care of, and then I could focus on doing like a polygon fiddler. X Dark Edge, thanks for the follow. So that's the idea. It takes a lot to get there, at least in the way that I've realized this, but it ended up being just a super fun project. So a lot of stuff may not be the most sensible way to do it, but it was definitely a really fun way to do it. So what this code does when we want to pack up the demo, we basically, the main parts is that we load up the Ableton project because we actually pull the data out of that. I think I mentioned in the one where I went over my 64K synth that we were able to just parse the Ableton Live project format to get data out of it. We do the same thing here for different kinds of track data for all the automation lanes that we had here. So we don't communicate with this over MIDI when we're actually packing the demo, because like when we're working with it, we don't need that, like it doesn't actually need to be that accurate. But here we actually need, like, every frame has to be exactly what we expect. So we load that project. Is that TKLN0? Thanks for the follow. We load the project. We create a new MU window because while we're packing it up, we're going to show this. In fact, I can actually kick this off. Ezzy Sig, thanks for the follow. So what this is doing, if I can get back to the code, let me see if I can do, whoops, wrong one. There we go. So what this is doing is we get a state generator, which is going to give us an object that will create all those states. And we literally, we just generate, we know the frame rate of the SNES. And so we just take time for all those frames and we generate a new state. And then we show that if it's been, I think every 20 frames we show that. And that's just so I can watch this as it goes. Fingerbib XD, thanks for the follow. So every 20 frames, we actually update the window so we can actually see what's going on as it's packing. Like rendering, exactly, like rendering a video in this case. And then, yeah, here's our FPS for everything. Where the bank starts, which that way we can make room for like the audio bank and everything. Oh, and look, when it's done, it opens the emulator. So nice. I think it also gives some kind of cool output as well, if I remember correctly. Yeah, it does. Gave us the total number of instructions it generated before and after a people optimizer that I have. I'll get to that in a sec. The total size of the generated instructions was about a meg, so that's one of the reasons why this works, by the way, is that when you generate all this bytecode for the entire demo, it's like a 3-minute demo or like a 2.5-minute demo or something. Then it basically, like, it ends up being a fair amount of data. But of course, on a Super Nintendo, if you go with like the maximum ROM size you would have had, that would have been like error appropriate, which would have been like a 4 meg ROM. We have a lot of space to spare for that, right? And the effect code isn't going to use that much space, so it makes kind of sense to have this kind of system. For something like a C64, it wouldn't, because you'd spend all your time streaming from the disk and unpacking. But this is just data and ROM, so this actually makes a lot of sense. This is the time it took to pack. This is actually linker output for all the different sections. You can see the enum test data is all the stuff that ended up being there, and then it's done. So you see in the compos, does this need to be in an actual cartridge ROM, or is there any reference emulator? So it depends. New was actually shown in emulator, but that was mostly for convenience for the compo crew at the gathering. Smash It was shown on hardware. And typically demo parties will prefer to do it in hardware, but they're really not that lenient. Or I mean, not that strict. Like if you talk to the organizers, they'll be pretty understanding, and emulation is not always the best option, but it's a fine option if that's all that you can actually get on site. But it's cooler to have hardware. So, in fact, actually, right beneath my desk, I keep a road case. With a Super Nintendo, controller, power, a flash cart, everything. So if I want to make SNES demos again and bring them to some demo party, it's all right here. That's a PAL SNES because I live in Europe. And to my right, over here, I have a couple Japanese ones as well. So basically always ready to go. Okay, so for creating the ROM, you use Ableton project files input. Yes, that's correct. I guess that now I think I understand your comment more. So it's not sitting there recording output from that in order to generate the output data, because we would have to like play it and we would miss frames as we played it from Ableton, so that wouldn't be very robust. So yeah, we just take that as input and then we sample the different automation lanes at regular intervals. So sampling the demo then would give us a bunch of these states for every frame. And then we have a second pass that takes 2 states and just gives us a little bit of bytecode that would run between those frames, right? And then you can kind of see how just a data pointer into these instructions would actually work here. So I can show you some of the code there. See you later, Vince. Yeah, no worries. So I think this is the player that plays the bytecode, by the way. We basically have the current adder and the current bank because we have to use multiple banks. Let me move this over here again. And there's some other things. But basically, yeah, we have a jump table for the different instructions. The loop itself basically takes, we know, I think it's in here. Yeah, this is the start bank offset. We don't use high ROM out of laziness. Yeah. Yeah, so coming in here, the A is going to be the current bank that we're going to start reading from, and then we have the current offset within that bank that it starts reading data from. Drew 2, no worries. This will be up on YouTube pretty soon. So basically loads the data pointer with a given position in the first bank. And it assumes that all the banks with the animation data are consecutive. So then what it does in the actual loop is, I think that's here in update. Set up some stuff to get an 8-bit accumulator. That's one of the really annoying things about 65C816, by the way, in this NES, is that you have to always switch between these 8 and 16-bit modes for the registers. It's super annoying. If it's running, we're going to branch into the opcode loop. Otherwise, we're going to return. So the opcode loop will just read the next byte, and it'll shift it left by 1. And what that does is it just, by multiplying by 2, we can basically just transfer that into X, and then we just use that as a jump table offset. So every address here, these are a bunch of different addresses to functions that will implement a particular opcode. And each one of these is 2 bytes wide. So if we take the number of the opcode and just shift it left by 1, which is this, we'll read the next byte and then shift it left by 1, transfer it to X, and then we can use it through this indirect addressing mode, which will actually just jump to whatever one of these there are. So each one of those, for example, the end of transmission, this is the one that ends it. So this is the simplest one. It basically stores 0 in this is running variable and then returns. But we have other ones, for example, like store byte. This is used to like change registers over time. So for example, we can fade in the screen by having these store register opcodes that will store into the screen fade register, or the screen brightness register, I should say. This will read the next word, which will get the address, and then it will also read the next byte, which will get the value to put in that address. Then it will store that byte into that word address, and then jump back to the opcode loop. Very, very straightforward. So what the program would look like for every frame is it would have a bunch of these opcodes that we would run, and then an end of frame or an end of transmission opcode, depending on if it were the last frame or not. And end of frame should just returns from this function that's called every frame. For example, for using this, I thought it would have been here in the main loop. Oh no, yeah, this just waits for an interrupt. So here's interrupt bridges. Which get from vblank. I'm a little bit confused at how this code fits together. But basically this is called every frame when we get the vblank interrupt. And I can't remember where it sets that, is what I'm struggling to find here. Here's where it enables it. There's a system in it, which basically just initializes the system to a known state, initializing the interrupt stuff, and then maybe just anim test here. This probably sets it. Yeah, here we go. Initialize the animation system by loading from this particular bank, and then we set the vblank to actually jump into this routine, which will basically save the registers, jump to the animation update, and then return. This would also, if we were running different CPU effects, this would also, actually, I think I would branch into those from the animation data, now that I think about it, but basically all it would need to do. Volgensen, did you ever do a version of this tool that works with more traditional real-time effects rather than pre-calculated unrolled register I/O? So that's exactly what I'm talking about when I say CPU effects. And I didn't actually do a demo that uses that yet, but the idea is that, of course, we will. But it always came to a few weeks before the demo party, and then just never ended up using those. But yeah, that is the idea, and the next one that we do will definitely do that, because I have a lot of cool ideas that should use this. But yeah. But I'm going to dispatch into those from this data as well. So like this data, the whole point is that it's going to handle scheduling, and it's going to handle putting the data that the effects expect to be in video memory in the right places in video memory, which would allow us to sync that a little bit with a little bit more comfortable control and everything. Another really good advantage of this is that if I want to pack up a version of this ROM that ran on a Japanese SNES, I wouldn't have to resync everything because all the sync values in live are synced based on seconds. So I don't have to do like new frame counts. I may have to adjust some things. For example, if I loaded a certain thing in memory over like 2 seconds, that may not have been enough. Like I may need to make that faster or slower in order to run on a different platform or run on different, run with different timing. And I would have the ability to do that, but I wouldn't want to do that by like frame counting and then just like, oh, I'll run this part of the demo and then I'll frame count 6 frames. Oh, that didn't work. Okay, let me recompile and then run the emulator again. So it's just a much better workflow. So you can kind of see where I'm going with this, which that's sort of the next step, but we haven't made it there yet. So, and that's also why I wanted to show this version of the tool before I showed our demo that just used video compression, because the video compression, like the funny part is that this this animation play stuff with these opcodes, this is exactly the same CPU code that runs in both intros or both demos. Both demos use exactly the same thing. The only difference is that we added OIM data and HDMA. Everything else is actually the same in both of them. It's just that in the first demo, we were short on time, so we just applied it to video compression, which was really fun anyway, and it's kind of fun that it kind of uses the same system. And the second one, we did, yeah, a little more interesting stuff using this same system. And also there was a transition from C# to F# there, which makes a lot of sense in this case, because basically what we're doing is like we have those state objects, and then we're going to transform diffs of those state objects into bytecode. And then we're going to do some transforms on that bytecode. So I've been talking a lot about that, and I don't think I've shown that stuff yet. So I've shown you Mammon machine graphics, which the C# code uses to manipulate pixels and those kind of things. I've shown you Mammon machine emulation, which contains the SNES state object and then like a way to visualize those states. Now I'm going to show you Mammon machine animation, and this is the package that will actually be able to sequence some of these. So the first thing we have here is an instruction. So the animation player is basically a bytecode interpreter. So the instructions here are those instructions. So you'll see, if we go back to the animation player, these are exactly the same implementations of these instructions here. Although I think, like here, the different HDMA channel things actually use different, like I have 8 different implementations of these, or 7, I guess. I think the reason I use 7 is because I think I block the first one out for transferring other data. So for example, we use DMA to actually move everything into like video memory. So for example, where is it down? Yeah, like load VRAM data. Basically just fires off the DMA with offsets and everything that loads from the opcode stream. And that uses DMA channel 0, or at least we use DMA channel 0 for that. So then you have the other 7 HDMA channels to actually do HDMA effects. So HDMA, for those of you that are not familiar, on Super Nintendo is basically a way to have the system change register values or other things at the beginning of every scan line. And we use this for a couple different things. So for example, I'll fire this up again. This effect, for example, uses HDMA to change the scale parameters of this. And also it changes the brightness in order to get this kind of like depth effect here. And there's actually hardware support for doing that if you set up the tables right. Wilkinson says poor man's copper. That's exactly what it is, because it's literally delta encoded. Like there's 2 parameters. One of them is a weight parameter, which will weight a certain amount of scan lines, and the other one is a value parameter. And then you set it up by also saying which like register that, or which address this will write to. And I say address rather than register because it really could write to anything. But you typically use it for just changing register values. So yeah, definitely a poor man's copper. But it's kind of cool to have support for that in this system as well. And there's some fun things about that. But yeah, so I think that's why I only have the 7 channels here and why they would start at 1. Because that would make sense, because you you basically then get, you don't actually get parallelism because they run on the same bus. But you at least kind of you kind of fire everything off at once, and then everything just works out. In fact, it can run multiple DMA channels at once. And you can have it running the DMA and HDMA at once, but of course there's priorities there. So I believe, in fact, I think HDMA actually takes priority over DMA, which would be the more useful combination, but I can't remember if that's true or not. Yeah. So that's what the instruction is here. So this is literally just an F# representation of what those instructions would look like. You can see that some of these, like end of frame, end of bank, end of transmission, all those things don't have, like those are just very simple instructions. But things like store byte have a couple parameters associated with them as well. So store byte will have an address that's going to store the byte into, and then it has the byte value. You can see the same with the different pref HDMA channel. Pref HDMA channel ref is an interesting instruction. So pref HDMA channel will have int byte, the type of channel. So int, I believe, is the number for the channel. Byte, I think, is the I'm not actually sure what this one is. Not actually sure. Adder channel type data. Oh yeah, of course. The HDMA, I think, can only work on a certain range of values. So the address is you can only express it with a byte, or you only need a byte to express it, I should say. And then the type of the channel, which I don't remember what that is. Oh yeah, you either have it write a byte or it will write two values, which I think end up being interpreted as words. I can't remember. Because there's a lot of these registers in this nest that are like, if you want to update an address of something, you actually write 2 byte values, and one will write the low value, and then one will write the high, but you write to the same register twice. So I think that's what this is. I don't remember if it takes 2 values though from the data stream and does that, but it probably does, because that would actually make sense. And then there's the array for the different things. Now what's cool about this, so that's a pretty like simple instruction to fire that off, but then the actual array of bytes when it gets encoded is just right like inline in the stream, in the data stream. So it just points to wherever the data thing is and then jumps over it for the bytecode. But then we have these HDMA channel refs. So one of the things that's actually really common, for example, with that same, did I close this again? Whoops. Do not mean to keep closing this. For example, this same effect here, we actually can quantize the different values that are used here, the different like basically scales of the different thing here to make the effect, if that makes sense. And if we quantize that, then we actually get a limited number of scan lines that this basically chooses from to do the effect. Now what that means is if we do HDMA that uses like a certain set of scales, which will give us like if you look at this I think this effect is called X vectors. And if we kind of look at it over time, it basically, because this is a square object, it only has to rotate 90 degrees before it looks the same again. And if we quantize that rotation, then we actually only get a certain, like there's a limited set of different HDMA tables that it will actually use, right? I think there's like 30 or something. And so what this version of this instruction does is instead of re-encoding all that data, it can actually just have a back reference to some other instruction in the stream. And the advantage then there is that we don't have to store that table data again if we just want to refer to that for HDMA. So there's a separate version of that. And that really cuts down on data rate. This is basically, stuff like this is basically the reason why Smash It, which was a much more visually complicated demo than new, was 1 megabyte instead of 4 megabytes. Because we could take advantage of these kind of things. And there are parts in the effect where I intentionally quantized values like that rotation in order to take advantage of this. We also have load palette data, VRM data, and OAM data, which is basically has an address and then just a big chunk of memory that we load into there. Now the nice thing about this is, again, we can generate this basically anyway. The things here are different like opcodes, because like when we have a semantic instruction, we need to get the opcode from it, for example, to write the different stuff, and then there's different, a bunch of different parameters there. Here we have serialize, so serialize into a bank at a start address with the previous HTML addresses and instruction. I don't know why it takes that, but there's probably a good reason for it. And then it'll just match on the instruction, and then, just add this data to the end of it there. MathK, thanks for the follow. Another thing that this can do is it can try to combine instructions. I don't think it's actually used in this file, but it's used by the next part of code that I'll get to, where basically if you have two instructions that you know will be consecutive, you can try to combine them. So for example, one instruction that loads a chunk of video memory, and then another instruction that loads a chunk of video memory, if the addresses and the memory that they're actually going to load are consecutive and they actually touch, then we can basically combine that into one load semantically that'll give us the same thing. So instead of two loads that load this data, we can just do one load that loads that data. And we want to find cases like that a lot. The original reason I did that was because when doing something like video compression, I found that it was actually difficult to, in a lot of cases, for the video compressor itself to actually try and handle those cases, because it had a bunch of other concerns that it was trying to do, like caching tiles and trying to check differences between those, and like it was complicated enough as it is. So it made a lot of sense to just kind of dump really dumb data and then have a second pass over the instructions that would actually optimize out the dumbness, right? And those of you guys who've worked with video compressors and compilers or compilers, I should say, should be very familiar with that kind of thing. Like it ended up being very sensible, and it made both parts very simple. But this is just a file that just has stuff for working with instructions. Then we have what we call the frame serializer, and this is sort of the bread and butter of the whole technique right here. So this is the thing that will basically take, I think the function is at the end, actually. It'll basically take, where is it? Or maybe, I just want to find the signature. Here it is, yeah. So it'll serialize a frame. So it'll take the last state and the current state. It basically takes two states. And what you get out of this is a list of instructions. So we basically have a bunch of these little functions here. For example, serialize, screen enabled, and screen fade, right? So we're going to do some like register encoding that'll go into this register and some basically diff checks. Now I'm pretty sure. Yeah, so this is sort of the idea. It's because this is written in a functional style. I'm trying to kind of explain what it does more than how it kind of moves data. But it ends up being that we end up writing these differs with not that much code. But the idea is that basically what this encode reg thing will do is it will basically allow you to get the data from both the old state and the current state, and then it'll compare those, and if they were not the same, then it will actually encode that register onto the accumulator that it's like the list of instructions that it's making. Otherwise, it just won't. So that's what you see here. And most of this stuff is actually just using that. There's a couple different variants that will just encode other things that aren't just registers, like tile locations. You can encode the write twice registers as well, and it will handle those. Serialize matrix stuff. But basically all this is doing is it's just doing a big diff of two different SNES states and then producing a stream of instructions that if you had the SNES in the first state, but you wanted it to be in the second state, then you could just execute those instructions. And there's a lot of these because there's a lot of different states. So here's the actual thing where it actually pumps an empty list through all these different encoders. And then at the end, it'll reverse that. And that has to do with the fact that it's a linked list and it's a functional language. So you push onto the front of it, and then you reverse at the end. Getting some details, but yeah. So once we have that function that can take two states and give you a list of instructions to go between those, then we have the animation serializer. So given a function that'll give us states, the start time, the length of time in seconds, I believe, the frames per second, and where the data, like which bank the data starts in, this thing will just start producing banks of data. Bunch of different chunks of data. So we figure out the number of frames. There's a hack there, don't worry about it. Figure out the number of frames that the demo's going to run. And for each one of those, we're going to take some initial state, which that's sort of the seed value, but that ends up being replaced by the next state. So we take our previous state and the new state, and we serialize the frame, and then we tack that onto this accumulator thing. So we basically literally just make a list of instructions between all the different states, and then we just concatenate those into one big list of instructions. After that, what we do is we do a couple passes on this. So for example, this combine pass is squash try combine. This is actually really cool with a functional language, is that this right here is the entire code for trying to compare instructions that are next to each other and then putting them into one instruction if they were combinable. That's all the code. We just need a function that, given two instructions, can maybe combine them, and we need this squash thing that will actually do the data moving. So this is the pass that will sit there and try to optimize instructions that way. This is the HDMA ref pass, so I went over that HDMA and then the HDMA ref variant of that instruction. And this is what's actually going to go and find all those back references and then encode those differently as well. So basically this will run optimization on the combined pass and the HDMA ref pass. When it gets there, we see the original length of instructions and then the new length of instructions. Then we actually put all those into banks. So we optimize this first, and then we take all of it and we try to just take all the different instructions and just dump them into banks. But then we have to insert these end of bank opcodes when we actually get to the end of the bank so that it will start from the next one. Because it has to do a little bit like the memory addresses in ROM don't end up being consecutive because we're using low ROM. In high ROM, I also think there's some cases where they won't be. So we have to detect as we're filling in these banks that we need to actually jump over a bunch of memory next time. And so we add a bunch of these end of bank opcodes into the stream as well. And then we have a list of banks. And I think these are just byte arrays. Big bunch of byte arrays. And I'm fairly certain that this module, it just takes a .bank thing. So this will just generate a bunch of code that will basically dump that bank data into a binary file here, and then include that from assembler so that it gets processed by all the stuff. And that's how everything gets packed up. So that's basically the idea then, is that we would figure out all the different states for all the frames in the demo, then diff all those to get this big instruction stream, put all that together, stuff it in a bunch of banks, and then every frame that the demo runs, we go and execute some of those bytecode or some of those instructions. Now again, the awesome thing about that is that then it basically just means we have to generate those states. Now eventually that also means that we'll want to also have CPU code that we jump into for some of these, but really that's just adding a couple other instructions. So for example, and here, the thing that actually plays this. So for example, like we could just as well, instead of like, in addition to have all of these, we can just jump to a subroutine, right? It can do a long jump into whatever bank. And we could totally have an op that would do that as well. And then we would just have to encode in our state objects that we want to jump into a certain routine for these frames. So that's really cool, and I really like this system, because then, like if we're doing CPU effects, we just have to hook that up. And again, that's the goal. But then in the demos that we ended up doing, because we were so limited on time, we ended up using this system in other weird ways. So like in new, we ended up writing a video compressor on top of this. Smash It again just does all the effects in F#, just as generating those state objects. So for example, now I think we can kind of go over some of the effects that are here. So there's a few different effects here. The original one is just the SNES logo that fades in and flashes a bunch. And one of the cool things that you can see as this runs, by the way, is if you watch the video memory thing here, you'll see it actually. So the starting state of the SNES is just like a blank slate. So the demo is set up to start there and then load the data it needs progressively. So for example, let's find the Elix logo, which is this effect. This track here is how loaded thing is. So this is the data amount. And if I like, here it's 0 and here it's 1, and you can do this and it'll load that progressively. Isn't that cool? This is one of my favorite things about this system, is that you can just do this stuff. And you can see that this parameter increases over time. So the way that works is I have this function that just like, you have a certain buffer of memory that's supposed to be somewhere, and you have a scalar from 0 to 1, and based on that value you only load a certain portion of the bytes. And what that ends up doing when you animate it like this is, you can see, because it starts from the beginning and then slowly fills in, it just represents like this logo being 50% loaded at this time and then 100% loaded here. But then because of the differ, every frame you only get a few like a little bit of that data that comes every time, if that makes sense. So we use this to, over time, load different amounts of this data. The alternative to this would be, we would have to like determine how much of this we could load by hand in the background while producing another effect, or we would have to have a couple frames that just didn't show anything. And so in this case, we actually do use it to load in the background of another effect. Not, of course, for the first one, because we start with a blank slate. So we have to load this data initially. So the screen doesn't fade in until like here, you can see, right when it finishes loading. But yeah, so this will load, then the screen will fade in, and then we get the logo. And already by the end of this, we start loading this stuff for the next effect. So that's sort of the big motivation for this, is that I didn't want to do all that frame counting and loading by hand. I wanted to be able to have this stuff be dynamically loaded. So what it's actually loading here at the end here is it's loading up this face image here so that we can just flash into the next scene. And I'm so excited, by the way, to use CPU-based effects in conjunction with this system, just because of how powerful that is to be able to control the loading like that. So it's awesome. John Hunter 9, so the music starts instantly? Yeah. It should actually be possible to just create like the first frame state and just like diff that before we start playing music and stuff. I can't remember why I didn't do that, but probably just short on time. Anyway, after that, this starts displaying, and you'll notice that there's a few frames before it displays the credits. You can see it actually loads that image and then displays that, and then it'll go back away, and then it unloads and loads the next one. See that? And you'll see that happen again. And this will go off screen, and then we start, or actually here we just do some palette manipulation. It'll start just loading a ton of stuff here, because this effect that comes next is mode 7, and mode 7 has basically very particular data layout that it needs to conform to. So we have to load a lot of data to show this effect that should be showing here. So this is one of the problems with live, is that a lot of these values just don't get sent. So I need to replace this by the time we use this again. But with a better tracker, this will work better. We also control things like the mosaic effect that's on the SNES as well for those states. Figure out how much it is. There's a couple sync bugs here that were just accidental. I don't know how they happened in Ableton, but I didn't have time to change them out. But that's just in the demo. But yeah, so for example here, we fade out the upper and lower logos, because then we start fading in the graphics for the next part. The next part comes in. There's actually a couple different background maps. I guess I can go over the details of the effect in a second. Then we have this effect. And it's really just cool to see, like, here you see the palette manipulation here to get the splashing. It's just so cool to see this stuff loading and loading. And also was not very fun to manage. Even though we had this system, it was still kind of a pain. Just because it is a pain to organize this stuff. But it ended up working out pretty well. Here it's loading a lot of mode 7 data. This background in particular. Big sprites. There's also some rendering glitches on the hardware, by the way, for this effect. And that's actually because there ends up being too many sprite blocks per scan line here, which the hardware can only handle to some effect. So a lot of these ones on the side end up being cut off. That is actually deterministic, and one of the things I need to cover in our little emulator here, because it is known how that will be affected. Just I know how to do that. So the other thing that's really nice about this is like we have HDMI channels on this effect, and all they do is like have little fades here. And it's so nice to write that stuff not in like an encoded assembler, but just like to write a data structure that represents that little fade, you know what I mean? Just a little bit more convenient. Just a little fade at the bottom. So much of this is going to be so nice when we start using it. And the memory is just a mess at this point because there's been so many effects loaded on top of each other. Now we're going to load this last picture here and show it. So you can kind of see how this is to work with. So I was thinking that I would use this stream to first of all, this is the tooling that I wanted to show, but I thought I couldn't really show it without the demo. But now that it's been an hour and a half, I think I can actually. I think what I'll do is I'll basically take questions and stuff now if you guys are curious about more how this works, and I think I'll go over the individual effects that make up this demo next week, because that works a little bit better with my scheduling anyway. I got a couple weeks before I start taking weeks off for revision. In fact, I have this week and then 2 more demo scene streams. And so it would actually probably work out really well if next week we went over the demo effects here. And then the following week we would do new. Because I totally underestimated how long it would take me to explain this again. I wish I could come up with a simpler way to explain this, but I don't know, I'm just unable to do that. So yeah, sorry for the little cliffhanger, but I think that'll make the most sense. Because then we'll kind of get these in a little bit better, like more consumable chunks. I think it'll make sense that if we do it that way. And it definitely works better for me, because if I start digging into the effects now, I'm going to be here for another hour and a half. And I don't want to do a 3-hour stream on a Sunday. But anyway, this whole thing is a work in progress, and other than the fact that the sync tracker here, that the hookup with live doesn't really work very well, I'm wondering if there's some Max for Live stuff that could be used that might be better. They would use like OSC or something that would probably work a lot nicer, or just Rocket. But I wanted to have better control over curves, I think is why I wanted to use something like live. But I just thought that'd be cool. And it was pretty cool to work with this, but the main problem is like when switching some of these effects, sometimes the track values are a little bit off, and that ends up being a problem when some of the track values control how much data is loaded. So you get a lot of glitches when actually working with it in live, but it's still pretty nice, in particular to do a lot of these flashes. And next week I'll show you what tracks there are here and how, like, what exactly we controlled here, and then some of the data behind the demo as well. So that'll be fun. Daniel Colin, hint, add curves to Rocket. Yeah, your words, not mine. But I really want those. Studio C, I'm just a bit curious about the Japanese. Is it an aesthetic choice, or is there something behind? I saw there's Japanese in many of your demos. It's an aesthetic choice, I think. It's just something I think looks cool. I watch a lot of anime. In particular, a lot of sci-fi anime. Like the group Logicoma is actually from the Ghost in the Shell Arise series, which is really, really sick. And in fact, the logo is actually the head of the robot called Logicoma. Pretty cool. So does Rocket use MIDI as well? No. Rocket uses its own little network protocol over sockets, which ends up being a lot more robust in cases like this. Because what's happening here when this gets out of sync is basically that this is just sending MIDI data as it changes in these. Like all these things are mapped just to MIDI output. So you can see as I like scroll. Where's one that changes? See this little dot light up here? Maybe you can't see that. But that's when live is detected a change that needs to send a MIDI data, and we just parse the MIDI data and just, oh yeah, that was this track with this thing, and stuff it in a table. But it sends sometimes the checking for whether or not it should send the MIDI control value is not that robust in live, and sometimes it'll send them out of order, and yeah, those are the kind of problems we have. But with Rocket, it's a lot more strict. If we use something like OSC, it would probably also be a lot more strict. But we would have to do some Max for Live stuff to hook that up, and yeah, something I didn't end up doing. Data calling Rocket is quite battle tested for quite complex demos these days. Absolutely, it's a really good tool. The only thing it lacks is curves, better curves. John Hunter, what does Logicoma mean? Is it anything special or just Logicoma? I think it's logistics conveyor machine. So we actually put that in the demo we did at Solskogen last year. Why am I blanking on the name? Almost Infinite. It was in Almost Infinite. We had that flash. But yeah, it's an aesthetic choice. It's just something that I like visually these days. For a few years now, apparently. But yeah, when we do SNES demos again, we're still going to be using this tech. We'll probably swap out live with something else. Might be Rocket, might be something else. It might even just be live with yeah, like better integration for actually sending this data rather than MIDI, because I think that's actually the heart of the problem. Like if we had a bunch of tracks that would just read in automation value and then give us OSC signals or something, then I think that would work. So I'm sure that there's ways to do that with live, at least with Max for Live. John 109, can we watch the demo again? Of course. I want to build it again because I think it's really cool to watch. And then we'll watch it in real time when it's done. But yeah, the music for this, again, was done in that same tool that you saw last time. And I haven't really, so I haven't touched this tooling since this demo. I did do a bunch more work on the tracker, but I don't think a lot of it really came to fruition, because it was a lot of work in like exploring if rewriting the data model in Rust would make sense, or like if doing it immutably would make sense. And there's a bunch of things I'm exploring there, but haven't touched that in a couple years either. But we do plan on doing more SNES demos, and we will incorporate CPU-based effects into those as well, just because that was kind of always the goal. And I've had some ideas since like May of 2014 that have just been sitting on my hard drive as Photoshop mockups that will totally work and just be awesome. I don't say that to brag. I just say that because I'm excited about it. Oh, there we go. So eventually we'll get to that. Yeah, Citrix is a wizard. Alien also is just super talented. Like he all the different graphics that we have in here, plus a bunch we didn't use. I'll show a lot of that next week. He did so fast. Like most of this demo came together in like 3 weeks. A lot of that was spent finishing the tech. Finishing the tech and just organizing all the other stuff that was happening, like the graphics and the music. One of my favorite things about this demo too is like we got I wouldn't say a lot of crap, because generally both demos were really well received, I think, and I'm very happy with that. But we did get some flack, of course, for the first one being video compression for the visuals, mostly based on principle. And the funny part is when I released this one, those same people were like, oh, hey, no video stuff. And the reason I think that's funny is, yeah, that's correct, but we use delta coding on SNES state objects rather than delta coding on frames. And the replayer is like exactly the same. So I thought that was a bit funny. But yeah, the next one will be really cool. It's just it's kind of not that motivating to do SNES demos right now because there's just no one doing them. Like back when I did this one, especially, we really thought that there were a couple other groups that were gonna come out with these because there was people talking about them, but nothing ever happened. So it's like people were talking crap to us that they were gonna make a better demo, and 3 years later. I mean, I don't mean to like shit on people, but they were kind of shitting on us, and they didn't have anything, so. Vogenson says, you could argue a lot of the C64 speed code stuff is in the same vein. So I agree, and especially when we have, CPU effects to augment this stuff as well, then it definitely is. In fact, it's a way better way to write that. But yeah. This demo in particular, I don't really like feel cheap for using video. The first one was a little cheap that we used video, but we used it in a cool way, and unless you dug into the code, you wouldn't have known it was video, because there are very few visible artifacts, and I'm happy about that. So 109, they tricked you into developing for the wrong system. Yeah, that must be what it was. So, we'll do it eventually, but like right now, 64K is a bit more competitive. Kind of wanted to be a part of that. Yeah. But yeah, so I think next week we'll go over the effects for this demo. I think that'll be really cool. And the week after we'll go over new, which has both an OpenGL demo in it for the original effects, and then the video compressor that actually puts it on the SNES. Because that's the other funny thing about that one too, is that like I just made a 4-color OpenGL demo and made it play on SNES. Anyway, so this was fun, and yeah. So those will be my next 2 demo streams. After that, taking a 2.5-week break to work on revision stuff, and then we'll be back for more stuff. And of course, still got the emulator stream every Thursday as well. Arthur Carlson demo for the Virtual Boy. I have to do one eventually, honestly. Like coding, like doing the emulator for that platform made me really excited, because it has a lot of the same features that like the SNES stuff does, but it's better. Like it's just better hardware. It honestly seems pretty fun to code for. So I'll have to do a demo for that at one point. Cool. All right. Anyway, thanks guys for watching. Thanks for hanging out. And I'll see you Thursday or next time. Let's see you guys.